So, well, why is that we have that? Look, I look at this particular value, and I have that A1 should have color 1 and A2 should have color 0. So all that we're saying here is that they're different. But if we move to the next edge in the list that I have here, well, this one has color 0, so this must be of the other color, namely 1. If we follow this process, we can prove it by induction, but I don't think it's necessary. We can argue this. And then for every index that is even, CAI is associated with 0. So those vertices of index even will be colored with the color 0. Those indices with an odd index will be colored with color 1. So we will have that ACN is equal to 1. Well, why is that? Because n is odd. But look, I have that this edge is part of my set E. So the associated colors between these two must be different. Well, but that's a contradiction because we're saying that these two are equal. There we go. So now we have demonstrated that we cannot color a cycle with of odd order with two colors. And from that, we obtain the following corollary. Let G be a graph, and suppose that G contains a cycle of odd order. Then the chromatic number of G is greater or equal than 3. And the proof of this is very simple. Why? Well, suppose that you want to color G, but it has a cycle. To color a cycle of odd order, you need 3 colors. There we go. So the chromatic number of this must be greater or equal than 3. Now, another consequence of this theorem that we have here is that the complete bipartite graph KMN does not have a cycle of odd order. And why is that? Well, suppose that this contains a cycle of odd order. So that means that the chromatic number of this is at least 3. But we know that the chromatic number of this is 2. Contradiction. Well, another connection is that, well, not necessarily directly from here, but that is not so difficult to prove that I leave it as an exercise, is to show, we can show that the chromatic number of the complete graph of order n is exactly n. And why is that? Well, certainly if I have n vertices, I can just paint them all with different colors. But why is that we need all of those colors to be different? Well, think of the example of the triangle. A triangle, which is a 3 cycle, well, it's also a complete graph of order 3. Why is that we need 3 colors, right? Well, because all the vertices are connected with all the others. So the colors must be different. Now, we need to show that using different techniques, but still, it's one of those consequences of this coloring problem. And with this, we finish this position on this topic.